Hmm. Hey, hi. You must be here for the black hole seminar. Yeah, I mean, isn't this the room where it's supposed to be happening? But there's nobody here. Well, well, this is the room where it's happening, but there were supposed to be a lot more people in attendance. Uh, anyways, so how much do you know about black holes? Next to nothing. Oh, okay, nice. And there's plenty to talk about. Let's go to the presentation room and then we can start. So we can start with the mathematical definition of a black hole. You can see this, it comes from directly from Einstein's field equations of general relativity. So we can also move on to the size of black holes. They can be very large. In fact, all galaxies have one in the center of their galaxy binding them together. This is Sagittarius A star, the center, and the what was that? Are we in space? How did we get spacesuits? A quirk of the presentation screen. Oh, wow. Well, what better place to learn about the cosmos? But what just happened, though? Did we get sucked into the black hole? Oh, yes. Black holes have such strong gravity that even light can't escape from them. Hence the term black holes. No light can escape, so nothing to pick up. Okay, but how does that make any sense? I thought light was the fastest thing in the universe. If it goes in and doesn't come out, doesn't that mean it gets destroyed? Is that even possible? That's a good question. So, what the laws of electromagnetism say is that light is the speed limit of any information in the universe. If I wanted to send you a message, the best I could ever hope to do, without bending space, is to send it to you at light speed. Okay, so then isn't the black hole kind of like destroying the information of the universe? I didn't think the universe was like a CD where you can scratch it and lose information. And also, what do you mean by bending space? Oh, we'll get to that, but that's one of the many mysteries regarding black holes. If information can't be destroyed, then what happens when something enters a black hole? If it enters the event horizon, it's gone forever. Nothing could ever hope to send any signals. Okay, well, what's an event horizon and why can't I send any signals past it? So, the event horizon of a black hole is the point where light can no longer escape the black hole's gravitational pull. So, try to think of it this way. So, let's say we're both at some point in space near a black hole. We both would have cones of information that we can send and receive, since we can only send and receive information at the speed of light. Think of this as the areas in space and time where I can see you sending me a message and you can see me sending you a message. As I move closer to the black hole, the gravity causes my information cones to skew towards the black hole because of its gravity. It gets harder and harder for me to send you signals, and it also takes longer and longer for them to reach you. And eventually, once I hit the event horizon, I can't hope to send you any more signals. Oh, so it's like a one-way information vacuum. But then how did we even see them? Like, how do we even figure out about their existence? Have you heard of general relativity? The idea that massive objects, they don't actually exert a force on other objects to pull them, but they actually warp space around them. So if you can think about it that way, when objects are in motion, they always follow a straight line, but the straight line is on a curved surface. It is falling towards the earth. It's still going in a straight line, right? Think about how you can start in the US and I can start in Mongolia. But if we both walk up in a straight line towards the North Pole, we meet eventually. So, what do you think would happen if I shoot a bunch of light rays at something like a black hole? They all bend around and get all swiggly, so the rest of the stars behind and around the black hole get all fuzzy. It's like we can't directly see black holes, but we can see their effects. In fact, there are some really violent effects that black holes can produce. If a black hole has a lot of matter orbiting around it, the particles can get sped up to a sizable portion of the speed of light. Then, when these particles bump into each other, they release a whole bunch of heat and radiation and energy. In fact, that's how scientists first observed black holes. Wait, so how's that? Wouldn't this general relativity thing explain that they existed? Oh, actually, yeah. General relativity did predict singularities when one tried to solve its equations for very dense spherical objects, right? Infinities or zeros where they shouldn't be showing up. It was Schwarzschild who first did these calculations, hence why the radius it takes for an object to become a black hole is called its Schwarzschild radius. Wait, so anything can become a black hole?
Oh no.
Yeah, if you compress it enough. Take the common example of the Earth. The Earth's mass would need to be compressed down to a radius comparable to a pearl, though no black hole is actually made that way. Okay, so then how are they made? Also, remember hearing somewhere that they can be really big? So when really large stars run out of fuel, they implode violently. After these violent explosions, called supernova, the stars become a special type of really dense star that we call a white dwarf. However, if the white dwarf is too big, it collapses in on itself again and it makes a black hole. The limit on the mass for white dwarfs is about 1.4 times our sun's mass. After this limit, they just collapse in on themselves and become black holes. This last alone limit is called the Chandrasekhar limit. Believe me though, but they could be way bigger than 1.4 solar masses. How big are we talking about here? More massive than some galaxies. Oh wow. I wonder what it must be like to fall into a real one. Well, it seems like we're gonna find out. Thanks for the seminar.